We will start the program tonight with Dr. Dimosthenis Karatzas. Dimosthenis Karatzas és un català nascut a Grècia que ha començat la seva carrera en la física, com he dit abans, ha fet la carrera en física i després ha fet un doctorat en ciències de la informàtica, és doctor en informàtica i comunicació i actualment és el director associat del Center for Computer Vision de la Universitat Autònoma de Barcelona. Benvingut, Dimosthenis Karatzas.
Gracias. Thank you very much for the introduction. I'm a bit out of my comfort zone here because usually it's the scientists presenting the slides and now it's like the slides presenting us. So I'll try to ignore what's happening behind my back and explain you a bit of my trajectory, how I ended up in Catalonia and what I'm doing in the Computer Vision Center. So as the word says, computer vision is about vision for computers. It's about machines that see the world. What we're trying to do is translate what is vision, which is basically the process of understanding, of discovering from images what is in the world and where it is, kind of creating models for that computers can use to interpret the world through images. And that's something that is quite easy to do for humans. We have no problem. We kind of do it without thinking twice. We see around and we understand objects and seats and faces and chairs and lights. But for computers, it's a very difficult process. And it's doubly difficult because we don't really know, we don't understand very well how the human brain works and how the human vision works so that we can translate it into a program. No? So that's the kind of thing that we're trying to investigate in the Computer Vision Center. And my story, as all stories, start a bit from a different starting point. I actually studied physics quite a long time ago. And that's when I first tried to do something on computer vision when I put my first program together to understand, to analyze images of diffraction patterns. Diffraction patterns are basically what happens is that some images that you take with an electron microscope of light when it passes through crystals. It creates a very nice structures of light and rings and dots. And if you kind of measure where these structures are and the angles between them, you can understand quite a lot for the material that produced this diffraction pattern. So I did my first piece of software that tried to analyze automatically this kind of images, and then I ended up doing my PhD on computer vision in the UK. I changed country. So in the UK, what we were interested into was to teach computers to read. So a particular type of computer vision, not to see in general, but to see text and understand and recognize text. And what we were interested mostly at that point was to understand text in complex color images like the ones you find, for example, on web pages. You know? On web pages or spam emails, you know, or you have a lot of text. A big amount of this text is actually coded into the HTML code, but there is some text which is actually drawn inside images. And for a human being, it makes no difference. Text is text, and you can read everything, and you know that everything is fine. But for a computer, it's quite difficult because the computer can understand the written text in the HTML code, but unless you have a program that can go into the image and extract this drawn text that you find in titles, advertisements, these kind of things, you can do nothing with it. You cannot search it, you cannot index it, you cannot filter it. You know? So this is a difficult problem because. You know, it's so difficult that actually it's used to tell humans and computers apart. You know, I think you have seen these captures, these little images of text that you are asked to transcribe when you fill in a form. It's so difficult that you expect that only humans are able to transcribe these images, so you tell humans from computer apart. So this is a kind of software that we were trying to create back then. And obviously for that, because that's not a black and white kind of situation of black text on a white paper, we had to understand a lot about color and how color actually influences the perception process, etc. So I actually did some work on color science, and we set up a company that uses color perception to calibrate monitors. That's anecdotal. We can leave this out for this talk. And then I ended up here in Barcelona working at the Computer Vision Center. which is one of the biggest research centers actually which is focused on computer vision. We have about 120 people, and we do anything that has to do with interpretation of images and videos. So we do things like medical imaging. We understand, we have programs that kind of help in diagnosing things, analyzing X-rays and magnetic resonance images. We have cars with cameras that can detect pedestrians in the streets and other cars, and they can react to situations that happen in the street. We put cameras on drones that fly around. We understand faces and facial expressions and gestures and postures of people as they move around. And of course, we do machines that read, that understand text. So I lead the robust reading research group in the Computer Vision Center. And what we're interested in is understanding text in the real world. Text that you find, for example, in the street, if you go around in the street. We actually recently had a project called Text in the City. So we're not very good with names, scientists. Recognizing, finding what the text is when you are out in the open and urban scene is not the easiest thing in the world. So if I tell you, if I show you an X like that, or a circle in the street, can I ask you, is this a letter? It's a very difficult question. Humans are very good in detecting text, but they need context. So a thing like that might be a circle or might be a zero if there are more numbers before and after it. So the kind of things that we're looking into is how these kind of processes, which actually exist in the human brain, this is basically called perceptual organization, and is a process that we use to put things together and try to explain, find the easiest possible explanations for groups of things together, not for individual things, are the kind of things that drive this kind of research. So we create programs, for example, that kind of model these processes and try to find potential meaningful groups of things in the scene and try to detect whether they are text or not. And that's quite interesting because humans can do it in the same way. You don't have to be able to recognize, to read the text, to know that it is text. If I show you text in Alien, in Klingon, you can still tell me this is text. And we managed to have computer programs that do this kind of things and detect text in the real world. And other things that we do, of course, is finding ways to efficiently process images. We don't want to process the full image every time. If you want to do this in real time, it's not the best way to do it. So humans are pretty efficient with that. In the optical nerve, we have about 100 million bits of information coming through the optical nerve per second. And we have many mechanisms to deal with that.
So
one of them,
don't you come here and tell me that? Because I feel a little isolated, because we already arrived to the 6 minutes.
Here we are.
So, and it's very interesting what you are saying. And you were telling what? How many millions of receptors we have in the...
I wasn't talking about receptors, I was talking about quantifying the information. So it's about 100 million bits per second that comes through the optical nerve. But obviously we don't deal with all of it at all the times. We have many mechanisms to deal with that. One of them is that we move our head around and our gaze, and we select where to place our attention. And what we do is we look at a place, and then we jump. We do a saccade.
Unconsciously.
Well, attention is a very interesting thing because it has an overt and covert part. It has there's a part which you control, and there's a part that is not controlled really by yourself. So I can decide to look at all the different faces one by one, but at some point, a car passes by and blows a horn, and then I turn around and my attention has moved without me consciously moving it. So attention is an open research issue, and there are many models of attention and how this...
And I was wondering, because it's still a challenge for neuroscience
Yes.
to define, to know how it's working, all these processes of perception, especially because perception is not only about seeing the thing, but also is determined by learning, by experience, by context. So this is a huge challenge for you.
Yes, yes. But you have to be careful there, because we try to create models, and the models are inspired from the ways humans think, but in many cases they are not biologically plausible. They are not exact copies of how brains work. And there's good reasons for that, because we don't know how brains work, and it's very difficult to create plausible models, and especially when the size of things, when the size of models explodes, because we don't have enough computational power to simulate the brain. There are big projects, European projects, that go about recreating a model of a full brain. So that's not the kind of thing that we can do in the lab nowadays. What we're trying to do is peek inside and do some small attempts to simulate specific things.
And what would be the goals, for example, with the quantities of information that we have nowadays on the internet and digital contents? What could we do with a technology like yours, with this information?
There's a lot of things that can be done. We work actually quite a lot with what is called big data and indexing and retrieval of information from big collections. Imagine that you want to search for a particular type of object in all YouTube videos. That's the kind of magnitude of things that you could try to approach with computer vision stuff. You put a word there and you try to find all the frames in all the videos where this word appears. That would be a big data kind of program. And this big data question appears in a number of different problems that we deal with in computer vision is quite often.
And also language, the relationship between computer detection and language. I'm interested about that.
Yes, but language is kind of my specialty in this case. It's a kind of a special object because it's not like trees and fruits that have naturally occurred. It's objects which are designed by humans for other humans to understand. So there is something there in the design. It's actually been shown that text and faces attract attention, in a bottom-up way. So it's a very special type of object. So there's something in the design, there's something in the way that we react to this design that is quite special.
And I wonder if we as humans, I'm still comparing, I'm sorry, but we need experience and learning. Yes. I mean, to be,
of course.
Our computers do need to be trained and have experience?
Yes, training and what is basically called path recognition, and machine learning, which involves learning from huge amounts of data nowadays. It's all about that. And every day it requires more data and more complex models, and we are now at the verge of changing paradigm in computer vision.
What would be that change?
Well, we are moving towards what is called deep networks, which are basically neural networks of many layers. And to train
like the brain?
Like the brain, well, we're very far away from what the brain is, but much closer than we were 10 years ago. But nevertheless, with this kind of structures, we need huge amounts of data to train. So these are amounts of data that we cannot get very easily from the real world. In many cases, we synthetically create images in order to train things. Imagine that you want enough information, the amount of information that a baby would look at for the first 2 years of its life, for example, to be able to properly train a deep network. So it's impossible to get it annotated from the real world in an efficient way. So many times we create synthetically.
And how, I'm interested also in technology transfer, because you do a lot of that in your center. So what kind of things in real life that we can see have come from your research at the
Well, a lot of things. Computer vision is actually everywhere. We do things on cars that drive on their own. We do things on industrial quality control, for industrial processes. The particular case of text, we have a strong knowledge transfer area which has to do with printed documents and the analysis of administrative documents and digital mailroom applications. And the kind of things I'm more focused in, we have transferred on applications that you use every day to translate things. If you go on vacation in China, and you take a photo on the Chinese menu and you want a translation, that's the kind of thing of detecting text in the real world. We have applications for visually impaired people. And recently we did more mundane applications, like we recently did an application with gas natural to detect the consumption. With a mobile phone, you can take a photograph of your gas meter and you send here the reading in. So it's a wide range of different
and also
applications.
Medical applications.
Of course, loads of medical applications, and of course there the idea is more helping the medical doctor to take a decision than making the decision for him.
Kind of expanding our sensory limits, because we have limits as our sensory.
Yes, and more than that, trying to understand how medical doctors actually do diagnosis. So that's an interesting example where vision is used both ways, because when a medical doctor is looking at an X-ray or at the colonoscopy video, he's looking at some particular patterns, and not even the doctor can explain you what he's looking at. So what we're doing is we put vision the other way around, and we look at the doctor while he's looking.
Why is he taking these decisions or doing these diagnosis?
So there's an eye tracker which can tell us where exactly the doctor is looking at every. No? And then with this information, we can train computer programs to do the same thing. Or, even more importantly, we can actually
help the doctor
help
also.
amateur doctors do the diagnosis in the same way.
Like double feedback.
So, yeah, we do a lot of this double vision kind of thing.
Very nice. And I have a question here, because now we are in the moment of questions. Somebody says, where did your interest in the sense of visions came from? Have you considered to do research on the other senses, like taste, touch, of hearing?
Very interesting. Well, yes. I actually did some. While I was doing a postdoc in cognitive science in psychology department, we did a lot of sound and vision at the same time. It's very complex, and we are still very premature, no, to put a lot of things together. But it's definitely something that's going to happen eventually, and it's very interesting. Maybe we'll hear in the next talks about how babies understand language from hearing. So for me, it's also something which is very interesting, because it's all about the amount of information that a baby sees in the first 2 years, and that's where we are with computer vision at this point. So hearing is another kind of input for language, which is extremely important.
But it's kind of scary. The size of the challenge is kind of scary, because we are very far for understanding the brain.
But again, that's why we do science. We are permitted to fail. No, otherwise we will never manage to discover anything new. So yes, it's a far-fetched challenge. It's more of a technical problem to have the infrastructure to pull together this kind of research. But I think that every year we're closer to being able to create models which are complex enough to receive much more sensor data.
And how do you see the very fast? I mean, tell me, how do you see the future? What's happening in 20 years from here in computer vision?
Difficult to say, because computer vision is kind of going in cycles. Now we're back into neural networks, and that's something that we left 20 years ago. Now we went back to it. So it's going in cycles. I think that the next thing that's going to happen is to focus again on the context of things and trying to understand things holistically and not specific things. So instead of doing object recognition or text recognition or face recognition, try to put everything together and understand what's happening in the scene. That's something that we have.
As the brain does, as the learning process.
Exactly. So this is a kind of modeling the experience and using it to interpret things in a holistic manner. No? So the fact that I see chairs here probably tells me that I'm in a room where people sit and we discuss, etc. So that might influence the fact that I expect to see faces in particular places. So that's how the human vision works, and I think that this is the kind of contextual feedback that we would use to merge all the different atomic processes.
And do you think that the computers will overcome the limitations that we have, because our eyes have like technical limitations that make, and the brain does kind of magic to adjust these limitations. But
yes, I don't like this comparison, because I think we're comparing different things. The brain is very generic and very flexible in what it can do. And at this point, computer vision might very easily go above the number of neurons that we have in the brain. But at this point, we're thinking about specific processes and specific things that we're doing. So I don't know when we will be able to say that there is a vision model which is generic enough and can be adapted easily to do the range of things that the human brain can do. Although we might be very close to something which works much faster. We already have systems that work much faster and much more efficiently for very specific tasks, no, compared to human brain. So it's a comparison that it's difficult it makes little sense, no, as a direct comparison.
Very interesting. I think we arrived to our 18 minutes. I would like to talk to you other 18 or hours, but now is the time to receive our next guest. Thank you very much.
That see the world. What we're trying to do is translate what is vision, which is basically the process of understanding, of discovering from images what is in the world and where it is, kind of creating models for that computers can use to interpret the world through images. And that's something that is quite easy to do for humans. We have no problem. We kind of do it without thinking twice. We see around and we understand objects and seats and faces and chairs and lights. But for computers, it's a very difficult process. And it's doubly difficult because we don't really know, we don't understand very well how the human brain works and how the human vision works so that we can translate it into a program. You know? So that's the kind of thing that we're trying to investigate in the computer.
We will start the program tonight with Dr. Dimosthenis Karatzas. Dimosthenis Karatzas és un català nascut a Grècia, que ha començat la seva carrera en la física, com he dit abans, ha fet la carrera en física i després ha fet un doctorat en ciències de la informàtica, és doctor en informàtica i comunicació, i actualment és el director associat del Center for Computer Vision de la Universitat Autònoma de Barcelona. Benvingut, Dimosthenis Karatzas.
Gracias. Thank you very much for the introduction. I'm a bit out of my comfort zone here because usually it's the scientists presenting the slides and now it's like the slides presenting us. So I'll try to ignore what's happening behind my back and explain you a bit of my trajectory, how I ended up in Catalonia and what I'm doing in the Computer Vision Center. So as the word says, computer vision is about vision for computers, about machines. That my PhD on computer vision in the UK. I changed country. So in the UK, what we were interested into was to teach computers to read. So a particular type of computer vision, not to see in general, but to see text and understand and recognize text. And what we were interested mostly at that point was to understand text in complex color images like the ones you find, for example, on web pages. You know? On web pages or spam emails, you know, or you have a lot of text. A big amount of this text is actually coded into the HTML code, but there is some text which is actually drawn inside images. And for a human being, it makes no difference. Text is text, and you can read everything, and you know that everything is fine. But for a computer, it's quite difficult. The Vision Center, and my story, as all stories, start a bit from a different starting point. I actually studied physics quite a long time ago, and that's when I first tried to do something on computer vision when I put my first program together to understand, to analyze images of diffraction patterns. Diffraction patterns are basically what happens is that some images that you take with an electron microscope of light when it passes through crystals, and it creates a very nice structures of light and rings and dots. And if you kind of measure where these structures are and the angles between them, you can understand quite a lot for the material that produced this diffraction pattern. So I did my first piece of software that tried to analyze automatically this kind of images, and then I ended up doing my